Hello everybody, welcome to the next video in the series of Physics at Home. In today's video, we're going to be looking at magnetic field. More precisely, the direction of the magnetic field. Right now in this room, there is Earth's magnetic field. That magnetic field is about 46 microtesla. And that magnetic field is pointing in that direction, that's the north, as seen from this compass here. Now what happens if you bring another magnetic field in the vicinity of this compass? This here is a bar magnet. And for this bar magnet, it also has its magnetic field, which is leaving the red pole here. Okay, so it's leaving from here, and if we follow this compass needle, we can see that the magnetic field is like a curve around it here. On the other side, it's curved in this fashion. If we place it on top, we can see it here. So the needle is really getting tilted inside of it. If I bring it closer, we can see the needle tips in that direction. So meaning the magnetic field all around this magnet is in that fashion, and then below would be going in that way. So physics tells us that from the south pole the magnetic field lines leave, they turn, and they from the north pole they leave and then turn around and then enter through the south. Okay, so something similar to a bar magnet is a solenoid. A solenoid is nothing but a plastic pipe here around which a copper wire is coiled around. Yeah, the two ends of that copper wire are here. What we're going to do is we're going to have current pass through this coil. So it's going to enter from here, and then it enters here, and then this coil goes in this fashion, right? So the current is flowing in this direction, So if I take my right hand, then the direction of the current is the direction of my fingers. Then the thumb would be the direction of the magnetic field that this solenoid will create. Okay, this magnetic field, it's gonna come out, and then come over and then enter, right? Or come out and then in that fashion. So solenoid is nothing but a bar magnet, and the direction of these coils, or the direction of the current, is nothing but the direction of the electrons, orbitals of the electrons, which get preferential alignment in this bar magnet. In a regular material, there is no magnetism because the electron orbits are randomly oriented. Each orbit has its own magnetic field, but they cancel each other out. Having it aligned in this fashion gives us an understanding of how a bar magnet works, that inside this there are electron orbitals which are preferential alignment, and their magnetic fields add up. So what I'm going to do is I'm going to place this compass inside the solenoid in such a fashion that the compass is perpendicular to the axis of the solenoid. Yeah. So the axis of the solenoid is this way. The needle is perpendicular right now, meaning Earth's magnetic field is perpendicular to the solenoid's magnetic field. And what we're going to do now is turn the current on. So I have two meters here. This meter is measuring the voltage, so it's about 2.92 volts. Now right now there is no current flowing because the switch is open. Okay. And we can also see the way this arrangement is. Current comes in through the switch, then leaves from the switch, then the other end of the switch is connected to the resistor. From the resistor it goes to the solenoid, and then through the coils comes out from this end, and then this is connected to the ammeter. So it enters the ammeter, leaves from the ammeter, and then it goes back to the power supply. Alright, so we have voltage here. Let me just make sure. Okay, so this is aligned. Looks like it's okay. I think it is parallel or perpendicular. Okay. Alright, so we are ready to run this experiment. Let's close the switch. Watch the needle. It got deflected because now this needle is under the influence of two magnetic fields, earths and solenoids. And if we create, earth is like this and the solenoid is in that direction. So if we create a rectangle, then wherever the diagonal is pointing is the direction where the needle is pointing, because it has been pulled by both magnetic fields. So right now this is about 30-degree tilt, right? And the current is about 0.655 milliamps. Okay, so let's write that down. 0.655 milliamps, and the angle theta is 30 degrees. Okay, so let's increase the voltage. So we increase the current and essentially increase the magnetic field of the solenoid, meaning the needle will tilt even farther. Okay, so let's increase this to let's see. So I made it to, let's say, 40 degrees. Okay, and 0.973 milliamps. This is 40 degrees. And let's do one more. Oops, I think it had a little bit of back EMF. So this is 40 degrees. And this is a 1, slightly different, 1.00, yeah, milliamps. Let's get to 45 or 50 degrees. Let's see. Okay, so this is 45 degrees. And 1.278. So 1.278 milliamps is at 45 degrees. So we have these three angles now. And we know some properties about this solenoid. For example, how many turns are there over the length of the solenoid. And there is a formula where using the current we can calculate how much is the strength of the magnetic field inside the solenoid. So once we know the strength of the magnetic field inside the solenoid and the angle, we would be able to use trig to calculate the strength of the Earth's magnetic field. And then we're going to see how close does it get to the value that we know. Let's look at the next section.
Okay, so we saw that magnetic field of Earth is pointing north, and our compass needle was pointing in the same direction as well. And as soon as we place this inside the solenoid and turn the solenoid on, as in have the current flow through it, and the magnetic field of the solenoid also play a part in this experiment, then the needle tilts, correct, by an angle of theta. As you can see from the vector nature that the rectangle that is formed by these two are able to give us the direction of the needle where it is pointing, which is nothing but the direction of the diagonal. So this net electric field is a result of magnetic field of Earth and the magnetic field of the solenoid. So what we also saw that if we increase the current flowing through the solenoid, then the angle of the tilt also increases. Okay. So here at the top we have the equation for the solenoid. In this equation there are three items, mu 0, n, and I. Mu 0 is called the permeability of vacuum, which is a magnetic constant, which is 4 pi 10 to -7, and n stands for the turns per length, which in the solenoid that you saw, which is about 30,000 turns of copper wire, called per a meter of that solenoid. It was not a meter long, but that would be the average turns per length. And I is the current, as we see, and these were the three currents that were measured, and these were the corresponding angles. Okay, so now with this information, so now let's calculate what we expect the magnetic field of solenoid should be. And it was so let's see, B solenoid 4 pi 10 to -7 multiplied by 30,000 times current is 6.55 10 to -4. If we do this calculation, and it turns out to be 2.47 10 to -5 Tesla. That's the unit of magnetic field. Alright, so we have the magnetic field of the solenoid. Now we wanna, we have this. So let's calculate how much is this magnetic field of the Earth. As we can see, using the diagonal, we can see that there is a right triangle right here. For this right triangle, opposite to the angle theta is this side, correct? Opposite side, which is nothing but the magnetic field of the solenoid. And magnetic field of the Earth is the adjacent side. And opposite and adjacent, if we remember, in trig, make an appearance in the tan equation. So we know tan of angle theta is opposite over adjacent. Alright, so we know the angle theta and we know the opposite side. We want to figure out the adjacent side. So we switch the tan theta and adjacent side. So the adjacent side, which is nothing but magnetic field of Earth, is opposite side, which is solenoid, divided by tan of the angle theta. So 2.47 10 to -5 over tan. The first angle was 30 degrees, correct? And this turns out to be 4.28 10 to -5 Tesla. Now I checked for my zip code, and the magnetic field of Earth, standard magnetic field, was about 4.63. So magnetic field, which we can now use to calculate the percent error, which is the absolute value of magnetic field of the Earth minus the magnetic field of Earth, which is standard or given, divided by what we again expected is again the Earth, which is our standard, and it might change depending on the location. So it's a good idea to check it before you run this experiment. Multiply by 100, and if we work this out, let's see. So again, let me mention it here. standard. So 4.63 10 to negative 5 Tesla. So it's about 7.6%. Okay. So if I could, use a little bit more decimals than there are, I believe that this error could fall, maybe like 5% in range. But anyway, a single digit, percentage here. So this is how we can run this experiment, that using a solenoid, we can figure out how much is the strength of Earth's magnetic field. And to figure that out, we used the vector nature of the magnetic field of both Earth and solenoid. And using this triangular, situation here, we are able to apply a trick and figure out Earth's magnetic field. So this is how it works, and I hope you enjoyed the video. Next week we're going to look at vector nature of electric field.